All right, and this video is over natural logs. These are logs that have a base of a natural number. So the natural number is e. E is not a variable. It is like pi. There is a specific value for e, and it never changes. Okay, so just like pi is 3.14, e. Okay, if you go to the little pi button down here on your calculator, it brings up this menu, and then e is one of the options. If you go over and click on that one and hit enter, it'll give you the value of e. E is 2.72 approximately. All right, natural logs are one of the most commonly used, right up there with common logs. Once you get higher in math, natural logs probably get more used. The lower you are in math, where you are right now, you'll probably see the common log more. So it just kind of depends on the advancement of you in your math classes. Okay, so let's graph this and look at the inverse and see how this works. So we're going to graph e to the x first. I'm going to use the same x values I always do. All right, and since this number is so ugly, it's kind of hard to do, let's use our calculator here. So I'm going to go to the graph page. Now, when you type in e to the x right here, you don't have to use that e from the pi menu. There's a special e button here next to the 1. Next to the 10 to the x button, there's an e to the x button. So click that, and it'll do e to whatever exponent you want. So we want e to the x. All right, press Control T, and let's get some points going. All right, so I've got 0.14 and 0.37. All right, notice that e to the 0 is 1. Just like every other number raised to the 0, it's 1. Doesn't matter what that number is. Okay, e to the 1 is just going to be what e equals, which is 2.72. And then e squared, if I scroll down a bit, 7.39. All right, so let's graph these over here and see what we get. So -2 is 0.14, really close there. 0.37, not too much further. 0, 1, 1 and 2.72 be about there, and 2, that's 3, 4, 5, 6, 7.39, right about there. All right, so you see the shape is pretty much the same as all of the other exponential graphs that we've done. All right, and it's still got that asymptote there at 0. So the domain would be all real numbers, negative infinity to positive infinity, and the range would be 0 to positive infinity. All right, with the parentheses because it doesn't actually touch that asymptote. All right, and we also know that the inverse is found by switching x and y. So let me put all my y's here in the x row, and all my x's in the y row. All right, I'm going to switch colors over here, and let's graph these points. So I've got 0.14, that's really close here, and -2, so like right there. 0.37, -1. I've got 1, 0. I've got 2.72, 1. Then I've got 7.39, which looks like I'm around 3, 4, 5, 6, 7. It's a little off my video here. All right, and let's draw in our log curve. And it looks like every other log that we've had. Okay, its asymptote is the y-axis, the line x equals 0. So the domain for this log would be 0 to infinity, and the range would be negative infinity to positive infinity, all real numbers. Let's take a look at the equation. Okay, remember we've learned a way to switch around the equation. So if we write this as e to the x equals y, and then we switch the x and y, that's how you do inverses. So e to the y equals x. And then I'm going to use my little spiral here to convert it. So it's going to be log base e of x equals y. All right, but you never actually see it written as log base e. That doesn't really happen, okay, because natural logs have their own special notation. Okay, that special notation is y equals ln of x. ln, it's the Latin form of natural log. It's like logus naturalis, something like that. And that's the way that natural logs will always be written. So anytime you see an ln, it's the same as every other log. All the properties are the same. You solve it the same. Just remember it's the inverse of e. So if you want to cancel out an e, you use an ln. If you want to cancel out an ln, you use an e. Those kind of go hand in hand with each other. Okay, so let me show you on this graph here. Let's get rid of our table. All right, so if I type in ln, the ln button is Control E to the x. You'll see the little ln written in letters above there. So ln of x. And there's the graph that we had on our page. Also, I can type in log base e. I just want to show you that they're the same thing. So if I do Control log and I type in a base of e right here and of x, and it should overlap this red one exactly. And you see that it does. Okay, so just showing you the log base e and the ln are the same thing, but we never really use log base e. We always use the ln. So make sure to start feeling comfortable with the ln notation rather than log base e. All right, all of our properties are the same. So we're going to solve some equations and condense and expand some natural logs here. So let's solve this base e equation over here. This is an exponential equation. So we're going to start by kind of getting the e to the negative 2 by itself. So I'm going to add 5. So 4e to the negative 2x equals 8. And I'm going to divide by 4 because it's being multiplied in front. E to the negative 2x equals 2. All right, and now I'm ready to cancel out this e. So the opposite of e is a natural log, ln. So we need to do ln in front of everything. So this whole thing's going inside my natural log. But what's really happening is the ln and the e are canceling, leaving me with negative 2x. And then over here, I'm equaling that to natural log of 2. So all that's left to get x by itself, divide this by negative 2. And x will approximately equal whatever that is. So let's go back to our calculator, and we'll do the ln of 2 divided by negative 2. So I get negative 0.347. All right, so let's try one with a log. Okay, just like with the exponential, I want to isolate the log first. So I want to get this ln of 4x by itself. So I'm going to divide by 3, cancel that 3 out in front. So that'll be ln of 4x equals 8. All right, so to cancel out the ln, I need to do it as a power of e. So it's e to the power of ln of 4x, e to the power of 8. Okay, over here the e and the ln cancel, leaving me with 4x. And over here I'm left with e to the 8th. Divide both sides by 4, and I'll get what x equals. So e to the 8th over 4. So we can use this e to the power button here, power of 8. Make sure to arrow right and then divide it by 4. E to the 8th over 4 is 745.239. All right, this page we're going to take a look at some of the properties. Okay, so we just used a couple of these when we solved these equations, but right here, ln and e. Okay, if those two are opposites of each other, so they cancel each other out, leaves you with 0.15 t. Okay, here, same deal, the e and the ln, but this 3 in front is messing with us. We can't cancel them out yet. So use one of your properties. We can move that 3 up and make it an exponent. So this is now e to the ln of x plus 1 cubed. The e and the ln cancel each other out, so we're left with x plus 1 cubed. All right, this next one. we have two separate natural logs. So we should combine them together into a single natural log, and we can use the multiplication property. If they're adding two separate logs, we can multiply the arguments. That's what's inside each one of them. So e to the 2x times e to the x. All right, well, this is going to use one of those exponent rules we learned about. That we're multiplying like bases, so we're allowed to add their exponents. So this will be e to the 2x plus x, which is 3x. All right, well, now that I have a single log, the ln and the e's can cancel with each other, and that leaves us with our answer of 3x. All right, and then this one kind of works the same way as the one above it. We want to cancel out the e and the ln, but the 2's in the way, so I move the 2 up as an exponent. E to the ln of x squared. E and the ln cancel, leaving me with x squared. All right, one of the biggest ways to apply e and natural log in a problem is by doing a continuous compound interest problem. So we've done compound interest where it compounds like monthly or weekly or whatever. This one is like it's compounding continuously. It's always compounding the whole time. Okay, so it's got its own special formula. A equals P to the E, P times E to the RT. And all this stuff means the same thing it does in the other formula. This is the amount, this is your principal, that's the initial amount. R is the interest rate, and T is the time in years. So what is the total amount for an investment of $500 invested at 5.25% for 40 years, compounded continuously? All right, so we want to know the amount. That's A. Principal investment, 500. E is always going to be just E. Remember, that's not a variable. It's an actual number. And then the interest rate, move your decimal over 2 spots, so 0.0525. And then we're multiplying that by 40 because it does 40 years. So we just need to type that in the calculator right there. So we've got 500 e to the 0.0525 times 40. All right, and looks like that 500 after 40 years would be worth $4,083.08. All right, let's see what we have over here. All right, so we're going to invest $100 into a savings bond that yields 3.5%. How long would it take your money to double? Okay, so this one's a little trickier because it doesn't give us exactly the right things, and it's asking us to find something different. All right, not just finding A. We actually have to find one of the variables over here. All right, so it does tell us our initial investment. That's 100. So P is 100. E is always going to be E. Does tell us the interest rate, so 0.035. It wants us to figure out how long. That's T. So we're going to leave T as T. That's our variable we're trying to find. For take our money to double. So what's the amount going to be in? Well, if we started with 100 and we wanted to double, our money is going to be 200. So let's solve this out. It's like one of the problems on a couple pages ago. So I'm going to start by isolating the e to the power. So I'm going to divide this 100 out. So 2 equals e to the 0.035t. Okay, now it's time to cancel out that e. So I'm going to use the ln, natural log, to cancel that out. So I've got ln of 2 equals 0.035t. Divide this by 0.035 and we'll have what t equals. So that's ln of 2 divided by 0.035. So it's going to take 19.8 years.